Hi there. In this question, we are continuing with differential calculus from the previous video where we were looking at the November 2024 Maths Paper 1. Okay, so in question 9, we are told that there are points A and B, which are the turning points of this graph. So here's A and here's B. And then we also told point C is the y-intercept of this function f. Okay, so in 9.1, they asked for which values of x is this function decreasing. So we want to look at the gradient, or we want to look for a trend where as the x values are increasing, or should I say moving towards the right, the y values are decreasing. And inspecting our graph, we can identify that region to be from point A to point B. Everywhere else, the function is increasing. So our answer for 9.1 will be x must be between 1 and 5 over 2. So x and 5 over 2. And we will not say that it should be equal to 1 or equal to 5 over 2 because these are turning points and we know that's where the gradient is 0. So we can't include them. Okay, 9.2. Write down the x-intercepts of the first derivative of f. So the first derivative of f will produce a quadratic function. So that means where we have turning points, those would be the x-intercepts. And if we do a quick sketch of what that might look like on our graph, here we'll draw a dotted line. So this will be one x-intercept. And that will be the other x-intercept. And because we have an increasing cubic function, that means that our quadratic function will also be increasing. And it might look something like that. Okay, so that means that the x-intercepts will be at x is equal to 1 and 5 over 2. Moving on to 9.3, for which values of x will f be concave up? So concave up, that's where we see our cubic function having that valley type of area. Or it looks like a cup or a bowl, if you can call it that too. And looking at our function, let's pick a different color. Let's pick a green. That will be from the point of inflection, which is somewhere in between our two turning points, and going all the way till positive infinity because we don't know where it ends. So that's where it will be concave up. So we need to determine what that point of inflection is right over there. And the nice thing about the point of inflection, it's exactly halfway between our turning points. So to get the x value there, we just need to take an average of the x values of the turning points. So x at point of inflection will be given by 1 plus 5 over 2 divided by 2. And this will give you an answer of 7 over 4. So we can put that on our graph. So this is 7 over 4. But we don't know what the y value is, and we don't need it unless specified. So therefore, our function will be concave up for x being greater than 7 over 4. And that is our final solution. Moving on to 9.4, we were asked to determine the value of k for which y is equal to f of x plus k will have 3 positive x-intercepts. Okay, so let's first erase this, which was for the first derivative, because we don't need it anymore. So currently we can see that this function only has one x-intercept over there. And whenever you see f of x plus k, it means that this function has either moved up or down. So they want to know by what or how many units should this function be shifted such that we end up with 3 positive x-intercepts. So the x-axis is currently all the way down over here. So that means this function needs to move downwards for it to start coming into contact with the x-axis, which will allow it to have more x-intercepts. So let's start with this point over here, because anywhere in between, it's just going to have one x-intercept. So if I draw a line here, okay, let's try like that. This is us making an assumption that the graph has been shifted down by 8 units, because here y is equal to 8. So this distance is 8 units. And the moment it surpasses that 8 units, that's when we start seeing more x-intercepts, right? Because at exactly 8, we only have 2. So that would be, let's change colors, can pick purple here and there. And we wanted to have 3. So it needs to be more than 8 units. So let me draw a different line. Maybe I can use a pink. And let's say it's somewhere there. I don't know what that exact distance is. You can see now we see those 3 x-intercepts. There's one here, there's another one here, and there's another one there. So mission accomplished, right? But it's not over yet, because there's a limit. Extending our function to go somewhere there, which was not shown, we can see that if I then draw another line there representing the x-axis, so these lines represent the x-axis, assuming that our graph has been shifted further down, we see now that it only has one x-intercept once again. So that means there's a limit, and we can see that limit is at the other turning point, which is at point A. So that's sort of like our limit. So we can draw another line here like that, representing us having shifted down by that many units. And to get that distance from our current x-axis to point A, this is a distance of 9 units. So that means that anything greater than 9 units, the function will once again only have one x-intercept. So this means that this value of k, which determines how far up or down our function needs to move in order for us to end up with 3 x-intercepts, needs to be between 8 and 9 units. It can't be less than 8, and it can't be greater than 9 units. So that means in us writing our final answer, we will say that 8, our k has to be between 8 or 9. And it's negative because we wanted to move downwards. So that will be k has to be between -8. Well, -8 is bigger than 9, so that means we write -9 first and -8. We can't let it be equal to 8 or 9 because, again, that's when I said that we will have 2 x-intercepts whenever the the x-axis is touching the turning point, and we don't want that. Okay, that's it for question 9.4. Lastly, moving on to question 10. So this is an optimization question where we are looking at the calculus of motion. So here a cyclist rode from town P and stopped at town T. The speed in kilometers per hour at which this cyclist rode is represented by the equation S prime t is equal to negative 3t squared plus 18t. Okay, starting with 10.1. We are told that speed is the rate of change in distance with respect to time. Okay, this makes sense because S denotes distance or displacement. So 10.1 wants us to calculate the maximum speed that the cyclist reached on this ride. In calculus, whenever you hear the word minimum or maximum, it means that you need to get the first derivative. So for us to determine the maximum speed, we need to take the first derivative and equate it to 0 so that we can get the maximum speed. Once we have that, we'll then be able to calculate, it's going to get the first derivative will allow us to get us the time at the maximum speed, and then substituting the time will give us the actual maximum speed. So the first derivative will be negative 3 times 2t plus 18 being equal to 0. Simplifying this is negative 6t plus 18 equals to 0. Negative 6t is equals to negative 18. Dividing both sides by negative 6, we get t being equal to 3. And our units for time here are hours. So t is 3 hours. Substituting that into the speed equation, we want the speed after 3 hours. So negative 3 squared plus 18 times 3. And this gives you an answer of 27 kilometers per hour. That is therefore the speed. 10.2. Calculate the distance between town P and town T. Okay, so firstly, we need to get the time it's going to take the cyclist to get to town T. Once we have the time, we'll therefore be able to calculate the distance. So earlier on, we were given a note that said speed is a rate of change in distance with respect to time. And I told you that this S denotes distance, also known as displacement. So for us to get the maximum distance, we take the first derivative. So that is why we are then going to use the speed equation, equate it to 0, and then use the time we get to calculate the distance, because the first derivative allows us to get the maximum distance when we equate it to 0. Therefore, we're going to say max or minimum distance is given by the first derivative being equal to 0. And the equation is negative 3t squared plus 18t being equal to 0. So we can divide everything by negative 3. That will then allow us to just have t squared here, and the sign changes. And then here you've got 6. Being equal to 0. Okay, and here there's a t. Now we can factor out t. So t minus 6 is equal to 0. Therefore, t is equal to 6, or t will be equal to 0. I said 6 first instead of 0 first. Okay, so now that we have our times for the maximum distance and the minimum distance, we can then now try to get the equation for the distance. And currently we don't have the equation. So the distance equation is, you get speed after taking the first derivative of the distance equation. So if the distance equation gives you something like this, that means we can assume that the initial function, which is the one for speed, is a cubic one, since its first derivative is something that looks quadratic. Therefore, here we're going to say the original function for distance will be a t cubed plus b t squared, because we don't know what the actual function is. Then we're going to take the derivative, which will be 3at squared plus 2b multiplied by t. Now we already have this equation, so we're going to equate this one with the one we were given, which is this one, to solve for the unknowns. So this part matches this part. So therefore, we're then just going to say 3a is equals to negative 3. And solving for a, it's negative 1. And then for b, we'll do the same. So this part, this 2b, matches the 18. Therefore, 2b will be equal to 18. Solving for b, therefore b is equal to 9. So now that we have our unknowns a and b, we can substitute them over here to get the actual equation for distance. So s of t will be equal to negative t cubed plus 9t squared. Okay, now that we have this, we can substitute our time for the maximum distance. And time for maximum distance is time at t is equal to 6, because that's the bigger one. So s of 6 will be equal to negative 6 cubed plus 9 times 6 squared. Therefore, s of 6 will be equal to 108 kilometers, because we need to state the units. Okay, so just a recap. In this question, we had to calculate the distance between P and town T. And we know we can get the total distance by using the first derivative, because that's how we get our maximum and our minimum distance. And we were already given the equation for the first derivative, so we equated that to 0, and then we were able to get the maximum time, which matches the maximum distance, which is t is equal to 6. From there, we tried to determine what the equation of the distance actually is, because the one we were given was the speed one. However, we do know that the speed is a first derivative of the distance equation. So if the first derivative gave us a quadratic, it means that the original distance equation was a cubic. So then we use that information to get the derivative over here. Then we equated this first derivative of that cubic function to our given first derivative. Then we were able to get the unknowns a and b, substituted that into this equation we came up with, and then that's how we calculated our distance after the cyclist traveled for 6 hours. Okay, bye.